So it is amazing to have Paula Montoya joining us today. Paula has over 20 years experience in exploration and geoscience. She's currently research professor at North University in Colombia and guest researcher at Geoscience Center at UNAM in Mexico. So with all of her experience, it is going to be awesome hearing from her today about geometallurgy modeling with an update for the last 10 years. So I hope you all enjoy it. Please use the chat. You'll have a chance to jump off mute and we'll have some discussions at the end. And yes, thank you so much, Paula, for joining. It's just amazing having you.
Thank you, Jessie, for inviting me again to give this presentation today. So thank you again and good morning, everyone. Today, I would like to talk about the geometallurgy model and update for the last 10 years. So before to start to talk about modeling, I would like to start with this question. So, which is basically what is geometallurgy is. There are different kind of definitions, just I bring some of them to discuss it. For instance, this is geometallurgy is related to study to confine to mineral, mine, and metal. For example, in this definition gave some keywords like exploration of reserves, calculation, grade, dilution, depletion, stopping, process mineralogy, mineral processing, quality, finishes metal. As we can see, there are different kinds of keywords in this definition. However, they are not connected, they are disconnected. If we see the second definition, basically, this is the SGS definition. Geometallurgy is the integration of geological mining, metallurgical, environmental, and economic information to minimize the NPV of an ore body while minimizing technical and operational risk. For this second definition, SGS introduced some keywords like integration, mining, metallurgical, environmental, and economic information. So this is those words are very important because basically we see the third definition, geometallurgy. This is a definition from Walter 2005, which was basically the Amira, one of the Amira projects. Geometallurgy is a cross-discipline focused on investigating the fundamental relationship between geological characterization of mineral deposits and their impact on mineral processing and recovery. So in this third third definition, Walters put together the above words and make it more understandable. So this leads us to the second or this following slide, that when the geometallurgy form, in order to investigate when those words or those keywords were connected to develop or to understand what geometallurgy is. So in this context, for some, geometallurgy born in Russia after the Second War, the Russian call it geotechnological mapping. Then the others break into the different categories. Some people say that geometallurgy starts or born with the original mining. Other things that geometallurgy origin is associated to extractive metallurgy or start with the introduction or geostatistics. Some people also think that geometallurgy born with the use of supercomputing in geological estimation. So for GeoMet, in the first GeoMet a scientific publication, one in the 90s, and this came from Sulut for the Economic Geology journal, and Sulut said from the University of Concepcion that geometallurgy, the purpose of geometallurgy is essentially to develop means of recovering mineral values through ecologically accepted means. So geometallurgy was actually a start to put together the keyword connected in the 70s, and the 90s start to incorporate the various disciplines such as geology, mineralogy, mining, planning, schedule, and metallurgy associated in order to work together to develop better mining designs. So this leads to this slide, which is the geometallurgy areas. Basically, to conclude, the geometallurgy integration is the knowledge of different areas which are involved in a mining project. Some areas on, for instance, community, environment, leaching, blasting, recovery, and comminution. So if we work together with each of those phases or stages, we can develop sustainable mining projects. So in this presentation, I am going to focus only on comminution and recovery geometallurgy models in order to develop or understand and map the recovery and comminution variability into the mine deposits. Currently, in practice, the ore body models are dominated by grade and basic geology. When I say basic geology, I refer to classical or the first step in discovery, or when in mining, when we have core logging, visual core logging. So the necessity to obtain more information in order to classify those models in different variables, for instance, leaching, texture, liberation, and environmental, we need to put together, we need to develop more analysis, more detailed analysis in order to understand the basic geology or translate the basic geology knowledge into those variables in order to optimize and develop better comminution models. So in this integration, or in that integration, is the nature of the challenge of the geometallurgy model. Basically, geometallurgy work together with many disciplines and areas of expertise in order to produce arrangement models to improve optimization, mining, and economical models. Some of those areas of expertise are geology, engineers, metallurgy, mine planners that work together in order to develop those economical or mining models. Okay, so before to start to talk about a specific geometallurgy model, there are key questions that we should focus on in order to predict better on the geometallurgy models. So these focus questions are very important in order to identify the key issues and identify the key research objectives. The quick question help you to develop accurate plans. Some examples or classical key questions are: can we characterize domain effectively from core logging? What is the best way to quantify texture, capture the attributes affecting different operation in process? What are the key attributes is the best to stick with standard grain shape and size? What is the different needs for research and industry applications? So depending on the questions on the problem in order to solve the key issues, there is a general geometallurgy methodology cycle that we follow. The first step is the core logging. The visual core logging translates this visual core logging to automated textural mineralogy mapping or textural classification modeling. Then use those results as a proxy data to combine with a comminution or recovery variables to predict the comminution variability or the recovery variability into mine design and apply to mine planning. And then the cycle should be updated over the time. Each time the mine is growing or the different phases of the project mining is changing, the whole process of the geometallurgy methodology should be updated. So the base of this brick pyramid is basically the values or the base of this big pyramid is the visual logging. The core logging is the first step. Then different kind of tests should be taken. The test will be the proxies in order to estimate the geometallurgy variables, comminution or recovery variables. The difference of different analytical methods basically is the cost of the samples, the cost of to take the measure. Currently, there are different kind of methodologies, devices to be used. So the way to use each one of those tests depends on the different kind of deposits or mineral elements that people want to extract from the mine plan. So in geometallurgy, geometallurgy can be applied at different phases in mining projects, from the discovery to optimization. Basically, the difference of this stage or the application of geometallurgy depends on the key questions. And in this key question, we need to rearrange the overall geometallurgy methodology in order to answer the questions. There is a list of entities that currently or since 2010, 2011, 10, are working with geometallurgy. I put some of them in these slides, but the main or the key point of this slide is to see the integration between university, mining or industry, and software development, because geometallurgy is not just for the industry. Geometallurgy or industry needs the academy or needs the research in order to put together those proxy data to explain the variability into the deposit. So let's leave the introduction about geometallurgy and start to talk about the geometallurgy modeling for the last update from the last 10 years. So the first geometallurgy conference started in Brisbane, Australia, with the AUSIM International Congress. Basically, the words and the key words or phrases that for the first 5 years was start the discussion about what geometallurgy is or was, see the integration of geological, mineralogical understanding and how to use it as a proxy data. Also was the classical spatial analysis. And at that moment, more of the geometallurgy models and to explain the geometallurgy variability, classical spatial analysis was used, for instance, PCA, principal component analysis, factor analysis. Also, in 2010, 2009 was the initial core scanning analysis methods and devices, and the use of spectral data as a proxy variables. I'm going to show you some examples that were presented in the first International Geometallurgy Congress in order to explain those keywords or key phrases. So just I bring some slices for that conference. This is the data mine or KI mining software. They talk about the spatial modeling and optimization of geometallurgic indices. That research was a part of a MIRA project, which was one of the main projects that started working with geometallurgy in 2008. The aim was develop methods, tools, and deliver to predict measures of processing performance. The final objective was to measure in the resource model so they can exploit in mine planning and optimization. To generate the performance indices for each cell in the block model include metal recovery, specific energy, and throughput. They use some of indices to optimize mine design, schedules, and cash flow. So the methodology started with Kenny and Walters in 2008 with the MIRA project, the technical report number 1, the methodology to improve the ore characterization and predictive modeling and processing behavior. They use principal component analysis to divide samples into groups and classes with a similar geometallurgy characteristics. They also use multiple linear regression models and techniques to create classes and estimate the comminution parameters. Kenny also in their PhD thesis used the same methodology to estimate recovery parameters as well. The comminution parameters were used to estimate performance indices such as throughput and specific power. There are some similarities. There are modeling methods. There are some similarities between modeling processes, performance indices, and grades in a resource model. However, there are also some differences. When modeling grains, the attributes are sampled and attributed to the estimated. When modeling performance indices, the attributes that are sampled are used as a proxy for both intermediate indices and final performance indices. Both model types require homogeneity so that the properties with model are similar. The case study where that methodology was used was Cadia East, which is a copper gold porphyry deposit in Australia. They developed a spatial distribution of classes and 3D views, downhole composition, and indicator variograms to populate the whole block model. They developed the domain modeling as a manual interpretation. This is to take in mind this manual interpretation, and they also use geostatistical methods for categorical variables and trends analysis. They develop modeling for comminution parameters. They also develop modeling for recovery parameters. They use variography analysis of variability using conditional simulation. This also a second study where that methodology was used, was Red Dog Zinc Mine. At that moment, they used geostatistical analysis and estimation of the additional data, the assessment of class values to model cells use, again, PCA results, the estimation analysis of comminution parameters and performance indices based on linear regression techniques, and the investigation, or they apply geostatistical method to non-addictive variables. In overall, some conclusions from both case study was the first one associated to continuity of mineralogy classes, was the mineralogical classes from PCA showed good spatial continuity and can be modeled using geostatistical method for categorical variables. For performance indices for Red Dog, the indices are based on addictive variables, which can be modeled using standard methods. However, this won't be possible and not be possible in all classes. And the techniques such as class-based and simulation method are suggested for estimation block models for non-addictive indices. For bias on non-addictive variables, an initial comparison for modeling and estimate indices for Red Dog shows fair correlation, but more work is required to identify the existence of degrees of bias. For optimization planning and schedule, the real value to estimate performance indices is when the engineer uses the integrated resource and geometallurgic model for optimized planning and schedule. Something which is very important is as you can see in these examples, the main techniques were principal component analysis and linear regression techniques, geostatistics, in order to develop or construct the block models. Also, that methodology was used as a third sample for La Colosa project. La Colosa is again a porphyry gold deposit located in Colombia. This case study was presented in 2011 for comminution studies. Also in the same project for La Colosa gold deposit was developed to predict geometallurgical recovery models. So just I would like to go through the results or the methodology applicable at that moment for La Colosa project for comminution. Just I'm going through quickly to those slides. La Colosa is located in Colombia in Central Cordillera. It's a classical gold deposit, gold porphyry deposit with early diorite, which is the high-grade areas, is intruded by intermineral diorite and cut the wall complex with the late intrusion. Those bodies, those porphyry models and bodies are coating the schist, black schist and green schist of Cajamarca Formation. Basically, there is different kind of texture that La Colosa has. Also, there are different kind of alteration classical from porphyry deposits, and also different kind of mineralization. So the key point is put together all this information or all this data in order to predict the comminution variability. So in order to do this, we compare or we try to investigate or integrate the comminution variables bond and AB versus different minerals or tests which help us to explain the comminution variability. So that's why we use the methodology that Amira project developed in 2008. That was the geometallurgy integration, then geometallurgy process modeling based on classes analysis and predictive modeling. And finally, we developed a block model based on domains, wireframe, using geostatistics. For comminution process modeling, we use PCA at that stage. And from predictive modeling, we use a classical linear regression techniques. With the result of PCA, we developed different classes, the same as Cadia is and Red Dog and DED. Each of these classes was developed manually. This is very important because this model, we predict for each class different bond and AB values. As you can see, for AB, for crash variable, is almost 90% of accuracy. For bond is 70% of accuracy. However, this model at that stage was quite criticized because the model cannot be reproduced automatically because the classes were developed manually. So that's why we start to think how we can translate the geological model or the geological knowledge into the geometallurgy models using analytical techniques without manual selection. As you can see here, this is was the model for AB, for crush variable, and actually each domain represents the range of IB into the deposit. So the model was very accuracy, and also actually the company at that stage was Anglo-Ashanti. They use it for to develop and construct the mining plan designs. However, we start thinking about the best way to develop new geometallurgy model without manual interpretations. So that's bring me to the second part of this presentation. Since 2015 to nowadays, the keywords change a little bit. We'll stay with discussion about what geometallurgy is. This is very important because there are some difference from Australian definition or Canadian definition or South American definition. But the main point here that geometallurgy basically is the integration of variables to understand and predict metallurgy behavior, comminution or recovery or blasting or leaching behavior into the deposit. But since 2015, new key or different keywords start to talk in the research environment. Those words were artificial intelligence, big data, machine learning, which was to introduce for geometallurgy concepts. Also, there were more improvements on mineralogy estimations. Also, had been improving the core scanning. We also start to work with the spectral data in order to explain the geometallurgy model. So just in this presentation, I would like to show some example for artificial intelligence that Canadian Institute of Mining and Metallurgy Petroleum developed or start to work with. And then I would like to talk about the applying machine learning for geometallurgic throughput prediction as a case study using production data Tropicana gold mining complex. So I'm going to show you new improvements for mineralogy estimation that was applied in a project in Chile. So in artificial intelligence for geometallurgy, standard and communication between humans and machine, basically, the main idea was put in contact or trying to translate all this geology knowledge into numerical data and trying to teach a machine or a script or methodology to predict automatical geometallurgy models in order to improve the geometallurgy models, 3D models. So this was one of the first geometallurgy models used by artificial intelligence in 2009. Also in 2009, Angela Scone used geochemistry in order to develop geometallurgy models for La Productora, which is a breccias, associated copper, gold, moly deposit in Chile. So she used the knowledge of the geology knowledge, the genesis, the spatial distribution of the minerals, in order to predict the response on metallurgy. So the objective was model mineralogy across the deposit, classify the mineralization as oxide, transitional, and sulfide, and develop proxies for 3D extrapolation. So the idea was understand the variability and control the process behavior to predict the process response and reduce the risk. The main conclusion of this work was the first one was explain the example for early stage the 3D geometallurgy data informed by geochemistry. She used the calculated mineralogy from a site core. Also, she used some QXRD results to compare, to predict those mineralogy models. And she used a linear program models that which is actually we used in 2011 and 2014 for La Colosa and for Cadia, but the model was updated and currently it's more robust than before. So the accuracy model was higher than we used it before. And she also used that result in order to make our classification, density classification. For machine learning, to apply machine learning for metallurgical throughput prediction, this was a case study in Tropicana, also by Anglo Golachanti. They try to predict the throughput behavior based on a multiple linear regression techniques, and also they compare with neural network purpose, which is explained in this article. So as you can see in this graph, if you compare the multiple regression technique versus neural network, they are almost similar. The percentage for accuracy was very high, and the prediction also was concerned. So the geometallurgical modeling has been improving for the last, I think, 6 years, with improvement of machine learning, using different techniques of big data or artificial intelligence. So those are the main changes from 2010 to from 2015 or nowadays. This paper, this article was published in 2022. So to me, it's very important, this comparison, because before we try to model geometallurgical models based on basic classical statistic techniques using manual classification, and we trying to use sections and trying to translate our geological knowledge in geometallurgy model. And currently, nowadays we don't need to use those manual selection. Just with applying machine learning or big data will help us to develop more accuracy geometallurgy model. So this is the big input that or big changes for the last 10 years. So that brings me to the end of this presentation. I put in this slide the scientific knowledge applied to your deposit research, because, as I said before, it's very important to connect the the science, the academy with the industry in order to develop more accuracy models, because there are more technology, there are more devices, equipment, more information. Each the project, model of the project have too many data that we need to integrate in the best way in order to obtain better geometallurgy models, or map the geometallurgy variability into the deposits. So thank you very much. I don't know if there is any question.
Thank you so much, Paula.